Okay, so we started this new chapter on graphs last week. Uh, so for us, graph will be just a set of vertices 1 to n, and the edges will be pairs I comma j. And the types will be undirected graph, which means that ij is an edge if and only if gi is an edge, or directed graph where one of them may not be an edge. Then we had walk, which is just a sequence of edges incident on each other, right? So it is physically a walk. Go from V0 to V1 to V2 dot dot Vk. And walk is a path if vertices don't repeat. And a cycle is if your source and destination is the same, and no other vertices or vertex is repeated. Also, conventionally we will call V0 a cycle if it's a loop. Okay, so if k is equal to 0, then you need V0 comma V0 to be an edge. So we may or may not have loops, depends on the example. Then we have connected component of a vertex, which is where all can you reach from V0. And then we had some properties, like you could see that in an undirected graph, the connected components will partition the vertices into connected subsets, and that may not be true when the graph is directed. So in the directed case, it is not a neat partition, because you can go, for example, from 1 to 2, but you cannot go back. So depends on your point of view. So if you are drawing a connected component from 1, then 2 will be there, but if you are drawing from 2, then 1 will not be there. Right? So that messes up many properties and many algorithms. So generally we'll work with only connected, with undirected graphs. So let us now look at the implementation of graphs. So how do you implement? Like in a C program. So since this is a data structures course, you can assume graph to be a new kind of data structure. So what is this? So you have mathematical modeling we have already done. So now we have to do the implementation part. So as you have seen before, mathematical modeling may not imply a unique implementation. There may be different C programs implementing the same DS. So here, first one will be link based. So what happens in link based is, have you seen this before? How do you implement a graph as a link or an array? So how do you implement as a link? Yes, so the natural thing will be that in this orange graph, so when you are looking at, so basically there are n nodes, so there are n starting points. When you look at the starting point of 1, then you should just link all its neighbors. So 1 is linked to 2, and then another element is 3. And then the second starting point is 2. The neighbors of 2 are only 1. So 2 is linked to 1. Okay, so it will look different from the picture because it is a C program, so it cannot look exactly like the picture, but it will contain all the information. So this is called an adjacency list. So adjacency list of a graph G let's call it LG. So this is a list structure, but yeah, not quite the linked list you have seen before. Slightly more complicated. So you will have multiple elements. So this part you can think of as an array. So the locations are 1, 2, 3, dot, dot, n, and in each location there is a pointer, start pointer, which just gives you a linked list of all the neighbors of the start only. So for 1 you have all the neighbors of 1. Then this is neighbors of 3. And this is pointing to neighbors of n. Okay, and in no particular order. So neighbors of 1, whatever they are, like 2 or 3, you can have a linked list there starting at 1, 2 arrow 3 or 3 arrow 2, it will not matter, because we just are interested in linking all the neighbors of 1, right? So when it is 1 arrow 2 arrow 3, it doesn't mean that 3 is a neighbor of 2 also. There is no inner structure in the black part. And the red part is what are the n vertices. So how long is the list? When you look at 2 or 3 or 4, how long is the list of to which it points? Sorry? Yeah, it is the number of neighbors. So we call it degree in a graph. So 1 will point to a degree of v many. Well, it will point to a list which is of size degree of v. So degree of 1 many. So degree of 1 in the orange graph is 2, and degree of 2 is 1, degree of 3 is 1, degree of 4 and 5 is 1 each. Okay, so that is the length of this list. So let's just give an example. So if you have a graph, undirected graph, that looks like this, then the linked list or the adjacency list representation or implementation will be as follows. So 1 at location 1 in the array, it will be pointing to 2 and 3. And then a null. So 1 points to 2, 2 points to 3, and 3 points to null. Note that again, the order of 2, 3 is not important here. You can implement whatever you want, 2, 3 or 3, 2. What is important is the size of the list or the elements of the list of 1. Okay, because you want them to be exactly the neighbors. In 2 you will have just 1 pointing to the null. What about 3? So you'll have 1 and 4, right? So you can have in any order. And 4, okay, so this is the adjacency list implementation of a graph. So this part you can think of this as just an array. So it's an array of pointers. Okay, and each pointer starts a linked list. And the order of the elements in the linked list is not important. Okay, can you see that graph corresponds to a unique linked list and vice versa? You get the I mean, and also directed graph you can represent. So a linked list and a directed graph, they are equivalent representations. Is this clear? No information is lost or no information is added. So LG and G are in bijection. Okay, there is a one-to-one correspondence between adjacency lists and graphs. So this may not be immediately clear. You should, if it is not clear, you should prove it. So proof of this will basically be, obviously when you have a graph, you can immediately by definition draw the linked list, the adjacency list. And when you have an adjacency list, then you should, as an exercise, show that you can also draw the unique graph. Right, because you can just take, for example, when you see 1 has a linked list 2, 3, then you can just draw that part of the graph, one arrow 2, 1 arrow 3. And then you can go to 2 and you can see that 1 is a neighbor, so you can draw 2 arrow 1, which in this case will just mean that the edge 1, 2 is undirected. 1 arrow 2, 2 arrow 1, both are edges. So it's this undirected edge, and so on. You can complete the graph. Yeah, when there is no arrow, then it means that the arrows are both sides. So the other property is, what is the size of this implementation? Is this efficient? So given G, given the graph, size of the adjacency list representation is so remember, we'll use n to be number of vertices, m to be number of edges in the graph. So what can you say, how much space will it take? N plus m, right? Is this clear? So it's order n plus m, and it cannot be shorter. So this is a very efficient, it's an optimal data structure which captures your graph completely and uniquely and minimally. It just requires how many vertices you have, which is the red array, and then how many edges m you have, which basically decides the size of the linked lists. Sum of those is, so maybe that's another exercise for you. So what do you think is the sum of the size of the list sitting at entry I? What is this? This is 2n. Why is that? So this is, I mean, I'll just write here that this is less than equal to order of n. And you can see in this example that it's 2 times n minus 1. Okay, you have the size of the orange lists is 6, and that 6 is actually coming from 2 times 4 minus 1. And this is always true. In the case of undirected graphs, you actually get this formula that sum of the degree of each vertex is 2 times n minus 1. And in general, you have this upper bound of order n. I think there is a problem, yeah. It should be order m. Yes. 2m then, okay. For undirected graph, it's 2m. Yeah. This can be shown. The proof idea for this is just that, so an edge has two vertices, two endpoints. So an edge contributes a count of 2. So when there is an edge from I to j, when you look from I, it contributes, this edge contributes to the degree of I. And when you look at j, it also contributes to the degree of j. So when you sum up the degree, you are overcounting by a multiple of 2, the edges. So you get 2m. Okay, so you can prove this exact bound. This is a basic exercise after graph definition. But what we are using in the above data structure is that the sum of the lists is actually bounded by order m. So the orange part is order m, the red part is n, so it's n plus m. Okay, this is the overall proof. So this is an efficient data structure. So let's remember that. So the pros are that it optimizes the space. And it gives you all the neighbors. Okay, so minimum space needed in this implementation. And when you are interested in finding the neighbors of a vertex V, you just go to that array location V and immediately you will get all the neighbors. Okay, this is the fastest way to find neighbors. What are the negative points, cons? Can you think of one? Yeah, so just testing x comma y, whether it is an edge. Okay, just to test that, what you have to do is you have to go to the array location x, which is constant time, but then you have to go through all the neighbors of x to look for y. So in the worst case, this is order n. Okay, so this is not making you access an edge properly or most efficiently. You have to actually look at the whole list of x. So testing this takes order n. Okay, so these two things are kind of opposite. It's a trade-off. Whether you want to find all the neighbors of x, or whether you just want to check whether y is a neighbor of x. Okay, so, sorry? No, the number of y's is only n minus 1. There is no m here. Yeah, so it doesn't save on just checking an edge. It will again go through all the neighbors. Okay, so in both cases it is, I can write the correct expression that is more like degree of x, which is upper bounded by order n. Okay, so if x has very few neighbors, then that is the size of the linked list, so you will do it as fast, but in the worst case it can be order n. It can be n minus 1. Okay. So that's another observation to remember, that what you are getting here, what you are getting for V is degree of V. Okay, these are the lengths of the linked lists. So that is what this thing is, degree of I. So sum of degrees is equal to 2m. That's the formula for undirected graphs. Any questions at this point? So that is the most common, that is the canonical implementation of graph. Okay, this is what, unless otherwise stated, this will be the input. Graph is given as this. Okay, so if this is clear, then the next one is array implementation, 2D array based. So this is called adjacency matrix. So adjacency matrix of G is AG, and so this is basically with ijth entry one if ij is an edge, and 0 otherwise. Okay, so AG is a matrix of size n cross n, right? Because the I and j, they take values 1 to n. So it's an n cross n matrix where the ijth entry tells you whether that's an edge or not. So it's a 0, 1, it's a Boolean n cross n matrix. So let's take that example. So one has, so first row is, so at 2, at 3 and 0 at 4, and then so the diagonal entries are all 0 because there is no loop, self loop is not there. First row is that, second row is there is no 2, 3 or 2, 4, but there is a 2, 1, right? So this is the first entry in the second row is 1. And then in 3 you have 3, 1 and 3, 4. And 4, 3 is there. Is that clear? And these are the row indices, these are the column indices. Because it's a 4 cross 4 matrix with so many ones, rest is 0. So what is the size of this data structure for a graph? So size of AG is n square. Right? So no matter what edges, even if there is no edge, 0 edge, still you are paying n square. Simply because you have to make a matrix and fill 0 everywhere. Right? So this is a relatively stupid way of storing a graph. Okay, so generally we avoid this. So can you think of an advantage of this? Yeah, so the only advantage seems to be that the cons point there that checking whether there is an edge, I mean whether xy is an edge, is order n. That you can now do in order 1. Because this is a 2D array, so x comma y, you immediately, I comma j, you exactly go to that location in constant time. So x comma y takes order 1. Okay, so that negative point is now, that problem is solved, but it has much bigger problems because I guess you can still hear me. If you cannot hear, then you can shout. So the problem is that when you have a sparse graph, when there are few ones, okay, like there is maybe no one, still you are wasting space filling zeros. So that is the major negative with this data structure. So it takes order n square even if m is much less than n. That is, it's very bad for sparse graphs. And in practice, usually graphs are sparse. So for example, the social media relationship graph, it is never the case that every person is friend with every person, right? In fact, a person is friend with only few people. So when you look at the graph, it's the edges are not so many compared to number of people. So m is around order n in the relationship graph. Okay, so and that's a very big graph. So if you are asked to make a matrix of 6 billion cross 6 billion and then search there, so it's all a useless algorithm. So you don't want to use the matrix, the 2D array for that. So this is why in real life adjacency list is used. Okay. Okay, just repeating one definition that we did last time. So we'll say that vertex y is reachable from x if there exists a path from x to y. Okay, so we had used the term connected, that y is connected from x, but we can also use the term reachable from x. It means the same thing, that from x to y there is a path, just shortened here by an arrow. Okay. So our next problem is essentially to do with this which kind of y are connected from x, which kind of vertices are reachable from x, and then traversing the graph to recover all this information. Okay, this is the first thing that you want to do with a graph algorithmically. You want to know, for example, that if you are interested in person X, what is the clan of that person X, right? So what are the people who are friends of friends of friends of X, right? So that's the most basic information you want, first information. So that is the traversal problem. We call it traversal from X. Okay, so this term will just mean that you traverse the graph starting from origin X and find out what you see. store that information. So this problem is we want to visit all the vertices that are reachable from X. Okay, so this all is important. One we could find just by looking at a neighbor of X. That is just one step. Right? Now we want to actually do all the steps and find all the Y's. So that is the traversal problem. So our lectures will now be dedicated to lots of algorithms which traverse a graph, and then they recover tremendous amount of information from the graph given in adjacency list. Okay, this is what we will devote our time on, and hopefully this is what you will do in your quiz also. Okay, so let's start with the first traversal algorithm, which is BFS. So this is breadth first search. Or breadth first traversal. Okay, this is a very old algorithm. It's almost a century old, or well, 70 years, 50, 60 years old. So what it will do is in one step it will go to the neighbors, and then it will go to the neighbors of neighbors and so on. Okay, so friends and then friends of friends and then friends of friends of friends and so on. So it'll go in that direction. This actually we also saw in some example a few weeks ago, which we called creating a ripple. Okay, so it looks at X as an origin, and then it creates a ripple from X. So as the ripple traverses the graph, all these friends of friends of friends of friends are discovered, and their distances are measured and stored. Okay, so it's doing many things. It is traversing, it is finding the distance, it is finding the connected component. So for that we need to define some terms and some ideas before we can give the pseudocode. So first thing is let's say distance. So distance notation is this. Okay, so distance in a graph G from X to Y vertices. This is the least number of edges on a path. Okay, so remember this is a path, this is not a walk or cycle or anything. So the vertices are distinct, and you want them to be minimized. So what happens when y is equal to x? Yeah, so we will call that distance 0 because there is no edge. We are not thinking of loops, self loops here. So x is just a vertex, so x comma x, the distance we will consider it 0 conventionally. And then when you go to neighbor, then the distance becomes 1 and so on. So distance can be at most how much? No, it cannot be, it can never be n. It's less than n. It's n minus 1. Because if you have two vertices, then the distance is just 1, right? There can only be one edge. So it's n minus 0 to n minus 1. So that is also called the length of the shortest path. From X to Y. Okay, so this is the idea of shortest path. But will this be applicable in solving, let's say, the train or the rail route problem? Is it the same distance? It's not, right? I mean, there is no kilometer here. This is just looking at the presence of an edge. So it is not yet solving the practical problem of shortest distances on the road or on the rail network. So that we are still far away. Probably we'll do it in this course or the next course. So here we say that the edges are unweighted. Okay, there is no kilometer on the edge. The edge is either there or not. It's 0, 1. But you can as well put kilometers on the edge. And then when you ask for shortest distance, it becomes a practical problem. So this is still a baby version of the shortest distance in practice. But anyway, so this will give still a lot of information. So these are the basic properties, that distance is between 0 and n minus 1. N is always the number of vertices of the graph. And when it is clear what graph, I will skip the subscript G. So if you have a path like this, is shortest path from x to y. Then what is the distance from x to y? That is k. Is it k? Yeah, should be okay. Yeah, x to y is k, but actually what I wanted to ask is x to xk minus 1. What is that? That's a more important question. So x to y is distance k by the hypothesis. But what can you say about the intermediate vertices like xk minus 1? What is the shortest distance between them? Yeah, so less than is correct, but I will say k minus 1. Do you agree with this? Why is it exactly k minus 1? Why cannot there be a very different looking path which has k minus 2 edges? Exactly, you guys are smart, just not in the exam. Okay, so you already know that the distance is at most k minus 1 because you are given an evidence, you are given a path of that length. So it cannot be more than k minus 1. Now, if it is shorter, is less than or equal to k minus 2, then we can use it to get distance from x to y to be less than k. In fact, you have this formula. So distance, this is kind of the triangle inequality. So the triangle inequality tells you that you can go from x to y, x to xk minus 1, and then take a step and go to y. Right? So So you have this triangle. So the triangle inequality tells you that distance from x to y cannot be more than distance from x to xk minus 1 and plus 1. Right? And so if you are assuming, or if somebody gives you a shorter path for x to xk minus 1, then that's the problem you have. That's the contradiction you get, k minus 2 plus 1. So you have something shorter than k. So which is a contradiction. Okay, so that's the proof by contradiction that when you have a shortest path, every subpath is also shortest. Okay, so not just x to xk minus 1, but from anywhere to anywhere. So xi to xj, it is what? J minus I, right? So every subpath also has to be shortest, because if it is not shortest, then you can replace it by shortest, and overall you have a shorter path from x to y. So this is the subpath property. So shortest paths have shortest subpaths. Okay, you can just remember that. It's basically a triangle inequality manifestation. And so this helps a lot in algorithms, in designing algorithms. So now is the ripple idea. So the idea for breadth first search starting from x to traverse the graph to find these friends of friends of friends and so on, and also their distances from x. Precisely you want to find that. So this idea is you create a ripple at x, centered at x, and initially you initialize all the distances to be infinity. And as you reach some place, you update the distance. So start a ripple. Centered at x and expand out. So let's just see it pictorially. So you have x in the center, actually let me draw a graph. So you have x and u, v, and y, and there is an edge here, and there is a w. Okay, that is the graph. So when you create the ripple here, then this is how it will expand. So this is the, so as the ripple expands, it will basically give you an expanding set. So V0 is the set which is at distance 0, so that is only x, right? No other vertex is in V0. And all the other vertices, think of their distances as infinity because they are not yet reached by the ripple. So then next, as you expand it, it will touch these, and you will get the set V1, right? So that is at distance 1. So you are getting u, v and y now inside V1. Now W is still unreached, that is distance infinity. So when you expand from here, so expansion means that you look at all the neighbors of x, right? That is u, v, y. Put them in V1. Then you look at all the neighbors of u, v, y, all the neighbors of basically set V1. So in this picture, that is only W. Is that correct actually? Neighbors of V1 are? Well, neighbors of V1 is actually the whole graph here, because u's neighbor is x, v's is x and y, and y's is x and w. So actually the neighbors of V1 are many vertices, but you should not care about the ones you have already seen. Right? So when I say neighbor of V1, I actually mean something new. So something new is only W. That's the one which has distance infinity. So that is the one which will go in V2 as the ripple expands. Okay, so this is how it will partition the vertices into distances, distance indexed sets. So you have V0, V1 and V2, and you can see that the distances are correct. Because there is no way for W to be reached in distance 1. Right? If there was a way, then it would have been already in V1. But it was not. So which means that its distance is more than 1. So it comes inside in V2. Okay, so that's the basic idea. Just based on this, you can actually give a pseudocode to do BFS traversal and find distances. So V0 is the set X, V1 is the set U, V, Y, and V2 is the set W. So that is how the ripple grows, and some of the things you have to keep track of in the pseudocode is this distance, temporary distance. So initialize an array whose value at x is 0, and for all other vertices, you set it to infinity. Okay, so this is what you start with, an array big D which is of size n, initialized to 0 and everything else infinity. Okay, and this is the temporary distance, and then as the ripple proceeds, it will get updated. And the claim is that in the end of the pseudocode, you have all the correct distances stored in this array. So compute V1. V1 should be just the neighbors of x, right? Which you can do how fast? So remember, the graph is given in adjacency list, so finding the neighbors is very easy. So in the adjacency list, you go to this location of x and just read the linked list stored there. So in degree of x, you will calculate V1. And then for V2, you have to do certain things, which I will just write in induction form. So for Vi plus 1, what you do is so put W in Vi plus 1 if and only if W is a neighbor of something in Vi, and the distance stored in the temporary array should be infinity. Okay, so this is the kind of inductive or iterative approach. So base case V1 you know how to calculate. In fact, base case was V0, so that you have initialized. V1 also you can compute in one step. In general, now when you go to V2, V3, so for Vi plus 1, what you have to do is look at the neighbors that Vi's have, and amongst them pick those which have distance infinity. So that is a W which is definitely distance I plus 1. Okay, that's what we will expand upon in the next class and give you the subroutine. So this works out to a pseudocode. Okay, so we'll do that next.